So we've been finding the volume that comes when you revolve a region about a line. And so we were just here, and this is where I had to stop last time. So just a few minutes. Whoa.
They don't want Eric. They don't want.
Whoa. I got the.
They're just like, oh, just have a meeting.
Whoa. Okay, gotta mute y'all people. Woo. I don't know where I'll be honest with you. If I was trying to take a class with all that noise in the background, I couldn't pay attention. I wouldn't even know what she's saying. So that's why I try to tell y'all, get your place of habitation so you can focus. Because if you were in the classroom with me, we wouldn't have all that noise. Wouldn't have all those people in the background, wouldn't have all that stuff. We wouldn't have fire trucks coming down my driveway. So we got to try to focus here. Okay. So this is the problem. We're going to revolve this region about the y-axis. So first thing I want to do is draw a picture. All right, so if you have that card that I told you to get, the quick study guide, the quick study guide gives you an idea of what y equals 1 over x, what y equals 1 over x, or x equals 1 over y looks like. So this is the curve, y equals 2 over x, or x equals 2 over y. Okay, so y equals 2 over x equals 2 over y looks like this. And of course, there's another part over here that I'm not going to worry about. And the reason why I'm not going to worry about that is because they tell me y goes between 1. So I'm starting here and I'm going up to 4. So I'm ending here. So I'm not worried about this part of the curve down there, because even though that's the other part of the hyperbola, I don't have to worry about it. So this curve, we already know, is x is equal to 2 over y. All right, so now it tells me that I am revolving this about the y-axis. So I'm going to revolve it about the y-axis. That means I'm going to get the same thing on the other side. So I get something that looks like that. And then I revolve it. So I'm going to find a value of y. Here's my value of y. I will start here and go around and come back. And there is my disk. So since I have a very nice disk, I can see my disk is going to start down here at y equal 1, and it's going to end up here at y equals 4. So my volume is the integral from c to d of pi times r of y squared dy. I know c and d are 1 and 4, and I know the radius x, r of y, is just this distance. If that's y, this distance is just x. And for me, x is equal to 2 over y. So my volume is the integral from 1 to 4 of pi. And then I'm going to get 2 over y squared dy. Now, this is a very simple integral. If you find this integral to be difficult, you need to be in my office immediately. Okay, because this is an easy integral. Because after this module, we're going to do 4 modules. We're going to do 2-3 modules of integrals. And they're not all easy, and they get more difficult. So this right here, you should be able to do without any issues. So the volume is equal to, I'm going to pull the 2 squared out and get 4 pi. The integral from 1 to 4. And then this looks like y to the negative 2 dy. And then I'm going to end up with minus 4 pi y to the negative 1, evaluated from 1 to 4. And this answer just turns out to be 3 pi. Okay. How we doing, guys? So that is, and it looks like a bullhorn actually. So you would expect that, you know, you would have a circle up here, and then down here, there's going to be a circle that would, a big circle for this piece. So you would have something that's going to look like a bullhorn. Okay. All right. Good to go. All right, so now let's look at our next problem. All right, so the next problem is a little more tricky. So that's why I'm going to cover it. Oh no, I don't want to go there. I want to go here. Okay, so for this problem, I have to tell you what OAB is, and I have to give you the line segment. Okay, so I'm going to draw OAB. So OAB happens to come from the graph of the parabola. So I only need this. And you better act right. Act like you know. Oh no, you're not going to act right. Okay. Let's see here. Okay. So here we are going to take the curve OAB. So I'm going to draw this, which happens to be the parabola y is equal to x squared. And then I'm going to draw this line. And this line happens to be so this is OAB. All right. So B, as you can see, since it's a point on the curve y equals x squared, is the point O. I'll tell you what A is first. A is the point 2, 0. I don't know why A is so small. A is the point 2, 0, and B is the point 2, 4. Okay, and here is my region. My region is this whole yellow space in here. That is the plane region that is being revolved around the line segment OAB. I'm sorry, the line segment AB. So if I had a real line that went through here, what would the real line, what would be the equation of the real line going through there? What's the equation of that line? Hello? Equation of that line.
Y equals 2.
Almost. X. But that was very good.
X equals 2.
X equals 2. Awesome. Okay, so this is X equals 2.
That's fine. I want to stay online.
Okay, so this is X equals 2. And we're going to take and we're going to revolve this thing about that. So when I revolve it, I'm going to get something on this side that looks like this. So that's what I get. And I'm going to pick a value of y, and I'm going to start on the curve right here. And I'm going to rotate it around like this, and I get a disc. There it is. Once I do that, I know I'm doing the volume by disc method because I see the disc. I also know that the disc goes from here, from the ground all the way up. So it's going to start at 0 and go all the way up to the very tip. So I already know that my limits of integration are 0 to 4. So that's going to be my CD. Because my disk is moving like this. Okay, so I know that I'm going to have CD. That part I know. And then I also know that my radius, I need to find my radius. So my radius is this length. So I need to find that length. Okay, this is some point Y, and then this is some point X. So this point that I choose X, Y, here's my Y value. This is X. All right, so now let's figure out how long that is. So let's see, I have a line segment that looks like this, and it starts at 0, and it goes to 2. And then I want to figure out how long this line is. If this is 2 and this is X. So how long is that piece? How long is this little black piece?
2.
Johnny,
Divide by.
who said 2? Johnny or Ezekiel?
I said 2.
Which one of y'all?
Johnny.
Okay, Johnny. This whole thing is 2. Right?
Yeah.
This piece.
Oh, that piece as well. You want them together or just?
No, I just want that little pink piece.
That's 1.
How you think it's 1?
Because that first one up there is 2, so that X be like 0, 1, and then 2, and then I guess you just separating it.
Okay, so you made the decision to make that X be a 1. That X could be a 1/2. That X could be a 1/3. The X could be 1.9 or 1.1. So now if it's just X, how long is that little pink piece?
It'd be 2 minus X.
Okay, so it would be 2, this whole length. If I take this whole thing, that's 2. And then I subtract off this part, which is X, I get 2 minus X. Okay, so the length of that piece is 2 minus X. All right, so now look back over here at the picture. I have this length going from here to here, that's 2. And I subtract off this blue, I subtract off this piece right here. The only thing it leaves is 2 minus X. Okay, so now I know that that little black line, that radius, R is 2 minus X. But I'm solving this problem in y. So I have the volume is equal to the integral from C to D of pi times r of y squared dy. So this is r of x. R of y says I have 2 minus, and x is, solve for it right here. X is the square root of y. So x is the square root of y, since y is equal to x squared, x is equal to the square root of y. All right, so now I got an integral. Volume is equal to, Johnny, are you good? Do you understand that now? That's important. Do you understand why it is 2 minus x? Johnny and Ezekiel?
Nah.
Not yet?
No, not yet. 2 minus x.
Here's
I
my-
understand because we weren't going to be able to get a definite value because as you were suggesting, it could be any number. So that's why we just do 2 minus the variable and then we
Exactly.
solve for the variable later on.
So here's my ruler. It is 1 foot long. If I tell you x is 6, then you would tell me that this piece is 6 inches. But if I don't, if you can't see what x is, I just give you something, then, and I subtract that off, then you could say it's 1 foot minus whatever you subtracted off. But you don't know what that is. So it's an arbitrary value. Keep thinking about it, Johnny. So this is pi. R is 2 minus the square root of y squared dy. So this is pi times the integral from 0 to 4. I'm going to get 4 minus 4, the square root of y, which I'm going to write as y to the 1/2. Minus y dy. And this answer is 8 pi over 3. Okay, any questions?
Why are the variables considered C and D?
Why are the variables considered?
Or the limits of integration considered C and D now instead of A and B?
Oh, because we just normally write the integrals like that. We normally write, if it's in the x direction, we write v is equal to the integral from a to b of a of x dx. And if it's in the y direction, we usually write c and d because that's what we write. This would be
Okay,
y dy, yeah,
okay.
okay.
Dr. Lott, you completed the square there, right?
I
On the
did
step
not
where-
complete it the square, I foiled it,
Oh, you folded, okay.
yeah. Okay. All righty. I think that's it for that. I think I go on to, oh no, wait a minute, I got another one. Oh yeah, this is the one you guys are supposed to do. Okay, there's one you're supposed to do by, you guys are supposed to do. So I can take roll. Okay, this is the problem for you guys to work on. All right, and I am going to take roll. How do I solve this problem? What is the graph of y equal to x minus x squared look like? What does y equal to x minus x squared look like?
The graph.
Yes, if I graphed it, what is that kind of, what is the function? What is it?
As a function, would it be?
A line and half a parabola.
Yeah.
Okay, well, it's actually just a parabola. Okay, is it face up or does it face down? All right, thanks, Chuck. It's a parabola facing down. Okay. All right, so now, does it look like this? Or does it look like this? Does it look like this? How do I know what it looks like? What are the X and Y, what are the X intercepts? Where does it hit the X axis?
0 and 1.
Good. Okay, so this is a parabola that looks like this. All right, if you don't get that it hits at 0 and 1, you take y equal to x minus x squared and set it equal to 0. So you get x times 1 minus x equals 0. So you get x is equal to 0 and 1. Okay, so therefore, we now know that this is 0. This is 1. We're going to take a point, x, and we're going to revolve it about the x-axis. Get something that looks like a lemon. So when we revolve it, we're going to start here. We're going to go down. We're going to come back around. There's my disc. Okay, somebody want to give me the integral for this problem?
Would it be 0 to 1? And then
Okay, so volume equals the integral between 0 and 1.
and would it be pi x minus x squared to the second? I mean squared.
Okay,
Yeah, dx, dy, dx.
dx. Okay, that's the answer. R of the radius is literally just this height. So the radius is this height. And that is this function. Okay. So this is the volume is pi times the integral from 0 to 1 of x squared minus 2x cubed plus x to the 4th dx. So I'm going to get 1/3 x cubed minus 2 over 4 x to the 4th plus 1 over 5 x to the 5th. And that is going to equal, I think, pi over 30. Yes. Okay. All right, any questions? All right, so there's one last area. It's not small, I don't know why it's small. It's one last area that we have to do, and that is C from this section. And that's volume by washers. Okay. All right, so does anybody know what a washer is?
Those metal circle things.
Exactly right. Okay, so a washer is if you have to screw something in and you don't want the screw constantly rotating on whatever it is because it's turning, you'll put a little disc or a washer in there so that that prevents it from from destroying whatever it is. Also, you may put a washer inside a faucet. So I want to draw this. So a washer is one outer circle. And then it has an inner circle on the inside. Okay. And so what I need to do is I need to find the area of the washer. Okay, so we want to find the area of the washer. And I can do that by taking the area of the big circle minus the area of this little circle. Okay, so the area of the big circle well, the area of any circle is pi times its radius squared. So let's draw the radius of the big circle like such. Okay, so that's R. And the area of the little circle we'll draw like this. And that's little r. Okay. So the area of the big circle is pi r squared. And the area of the little circle, or the small circle, is pi times the little radius squared. And so that gives us the area in between. I could not stand coloring when I was a little girl. It was such a waste of time. And I could color within the lines perfectly, but now I'm in a hurry. Okay, so there we go. All right, so therefore the total area is pi r squared minus pi times a little r squared. Okay, so now if we can make them a function of x, so if now big R is a function of x and little r is a function of x, then we would get the area of the washer is pi times r of x squared minus little r of x squared dx. Oh, no dx, no dx, no dx, no dx, just that. Okay, so now if I have some washers and I stack them up alongside of each other, then I can get a volume. So my volume, which is the integral from a to b of a of x dx, for washers becomes the integral from a to b of, of pi times big R of x squared minus little r of x squared dx. Okay, so we need to apply this to a problem quickly so we can understand it, because right now it's just abstract. It's just something that doesn't have any application yet. Okay. So just like any other problem where we needed to see the disk, in these type of problems, you need to see the washer. Okay, and once you see the washer, then you're real clear on what method to use. All right, so this is our problem. Consider the plane region bound by the curves y is equal to x squared. I keep saying that, I said that last time. Y squared is equal to x and y is equal to x cubed. Okay, so if I want to graph these, I have y squared is equal to x. So that really looks to me like y is equal to the square root. X is equal, y is equal to the square root of x. And the other curve is y is equal to x cubed. So let's graph them. So here is y is equal to the square root of x. And here is y is equal to x cubed. Okay. So I'm actually gonna move these because this one is y is equal to the square root of x. And this one is y is equal to x cubed. So I see my little region. It's the region between the two. It tells me I want the region bounded between these two curves. All right. And it's revolved around the x-axis. Okay. So when I revolve it around the x-axis, I choose a value of x. There it is. And then I see what my blue curve is going to revolve around. So my blue curve will do something like this. And my red curve will do something like this. Okay. So when I revolve it, that's what I get. So now I'm going to go up to the, actually that blue curve is a little high. Which means the red curve is not low enough. There we go. That's a little better. Okay, so now I'm going to start on the curve and revolve like this. But then this has a point on this curve that will revolve like this. And oh my goodness, there's my washer. I see it. There's the washer. Okay, so now I need to find a couple things. My limits of integration. And then I need to find my two radii. So my limits of integration, I already see that it's going to start at 0 because it's right here at the origin, but I don't know how far out this thing can move. I do know it can move out as far as up to here. But I need to know what that value is, and I don't know right now. So how can I find out what that value of X is? How can I find out that value of X? It's where these two curves intersect, correct? So set them equal. So set the square root of X equal to X cubed. So you get X to the 1/2 minus X cubed is equal to 0. Factor out X to the 1/2. That leaves 1 minus X to the 5/2 is equal to 0. So X is 0 and 1. So this value of X right here is just 1. Okay, so I know my limits of integration. X goes from 0 to 1. Okay, so what's my big radius?
X to X3, X cubed.
Is that the big one or the small one?
That's a big one.
Okay, so let's look here.
Root X.
The big one goes from here all the way down. That's the big one. You see that? And that's on the curve, the square root of X.
Oh, okay, okay.
All right. And then the little one goes from here down. Okay. I think we're ready. So the volume integral from 0 to 1 of pi, the big radius squared minus the little radius squared dx. So that's pi times the integral from 0 to 1 of x minus x to the 6 dx. So that is pi. I'm going to get 1/2 x squared minus 1/7 x to the 7th. Evaluate between 0 and 1. And that's just 5 pi over 14. Okay. Any questions? Okay, so I'm going to show you what I showed the other class, if I can find it. Yeah. Okay, I went on graphsketch.com. Oh, that's not it. That's not it. That's not it. Where's Graph Sketch here? Nope, that's not it either. It is here. Yeah. So I went on graphsketch.com. If you've ever gone here, this is a great place to go when you're doing homework or something and you need a graph and you just can't think real quick. So on graphsketch.com, I graphed the two curves of the next problem, which is x squared plus 1 and x plus 3. So this is x squared plus 1. It's a parabola floating in the air. And this is x plus 3. And then I went and I saved the picture. You can click to download the graph. And so let's grab the next problem. Okay. It is find the volume of the solid generated by revolving the about the x-axis, the region bounded by the parabola y equals x squared plus 1 and the line y equals x plus 3. So I can go here, grab my picture, and pop it right in. Okay. All right, so it says we want to revolve the region bounded between the two. So that region is this region right here. So, okay, so that region I want to revolve around the x-axis. All right, so when I revolve it around the x-axis, the line is going to look like this. And then the parabola is going to look, whoa. That line is going through the wrong place, wrong line. That line should be going through here, this point, and this point. Okay, now that should be going, yeah, okay. And the parabola goes up. Okay, so I get the region down there. I'm revolving it around the x-axis. Pick an x. I like this x right here. It's up. I'm sorry, that x is the wrong x. I like this x right here. It's okay, makes me happy. And when I revolve it, I go to this curve and I go around and I get that. And then I go to the curve above it and I go around like that. And there is my washer. I see it. Okay. All right. What do I need to do next?
Set them equal to each other.
Okay. So I need to find where they intersect to find my region. So I will set x squared plus 1
Equals x plus 3.
and you will solve that and tell me what you get. Anybody?
So that x squared is minus x. Would that be x equals 4? No.
Yeah,
X equals 2.
right, x squared minus x minus 2 is equal to 0. So that's x minus 2 times x plus 1 is equal to 0. So I get x is equal to -1 and 2. And you can actually see that from this curve. Here's -1 and it goes up to 2. So my limits of integration are -1 to 2. Okay. All right, what's my big radius?
Y equals x plus 3.
Good. And my little radius, obviously, is the other one. Okay. Brian. Brian.
Yep.
All right, give me the integral, please.
-3 to oh no, I'm sorry. Yeah, -3 to I'm sorry, -1 to 2 of x plus 3 minus
Let's go back. There's the formula.
x plus 3 squared
Good.
minus x squared plus 1 squared times pi. Forgot the pi in front.
Thank you very much. Okay. All right, so this integral comes out to be 117 pi over 5. All right. We are a little ahead of schedule. How did we do that? Did I skip a problem? No, I did that one, did that one. Did that one. Did that one.
Could you scroll up just a little bit?
I can.
Thank you.
To the last problem, I mean, to finishing this whole problem.
Yeah, for this one, just the setup.
Okay. I didn't draw my radii, so here's my big radius. Goes all the way up to the big at distance. And then the little radius goes there. You can see it. Okay, any questions? Okay, Jose, did you get all that?
Yes, I did. Thank you.
All righty. Okay, next problem. Of course, I'm going to switch it up on you a little bit. Did I even give the other one a number? It's nice to not have to grade exams this weekend. Okay, so I don't give out practice exam questions because your book, which is online, every section has a whole bunch of questions. So the only thing I would be doing would be going there or to another book and copying down a bunch of questions and putting them together, and you guys can do that. So I don't generally give a whole bunch of reviews. I do have some reviews. I think I do have review questions for this class, but every time I give the review questions, students tell me the test is nothing like the review, which I think it is. So now I let students find their own problems. I can give you guys the review questions if you want, but that's what I get. That it looked nothing like the review. Okay, draw this region, please. Uh-oh, somebody wants the questions. All right, I'll give them to you. Okay, can somebody please draw? I want everybody to draw this, draw the region. And then I want one brave person to hold their picture up to the screen so I can see the region. Y is equal to x squared and y is equal to 2x. One is a line and one is a parabola. This is a very easy region to draw. All right. Okay, anybody want to show me their picture? Let me go down and see who's, uh-oh, I see nothing but black. Ain't nobody trying to show a picture. All right, Danielson. You just have to hold the paper up. Yes. Did you use graphsketch.com?
I used a different website. I used Desmos.
Okay, but that's fantastic. Awesome. Okay, that is the right picture. Okay. Okay, so the line y is equal to 2x. And then the parabola y is equal to x squared. Okay, and so when I do that, here is my region. Okay, and it says this region in the first quadrant, so I only know that they want that part, is revolved about the y-axis. So if it's revolved about the y-axis, I already know now I'm going to pick a y. There's my y. And then I'm going to have the same picture on the other side where it is revolved to. Okay. So when I do that, I'm going to start on the curve. There's 1 revolution. Oh, that's kind of flat, but nobody cares. And there's my washer. Notice my washer is horizontal. So I'm not sure who asked me the question, why do we use C and D? We use C and D just to indicate that we're going in the Y direction. So now my washer is going to move this way. Okay. Why didn't you do that? Here we go. So my washer is moving up and down. Okay. No. Thank you. Okay. So that means my volume has to be in Y. So now I know that my volume is going to be the integral from C to D of pi times big R of Y squared minus little r of Y squared dy. Okay. So what are my limits of integration?
Do you set them equal to each other?
Let them equal to each other. Okay, so I have x squared is equal to 2x. So I get x squared minus 2x is equal to 0. Factor out the x and I get x minus 2. So I find out that x is equal to 0 and 2. But this is a CD, this is a y, so I need to know what this value is. I know that x is 2 here. And if I put it in either one of those equations, I find out that that is 4. So therefore, my limits of integration are 0, 4. Okay, we're good. Now we need our big radius. Okay. I need my big radius.
Is it x squared?
Okay, we're almost there. So this is y is equal to x squared, right?
Yeah.
But it has to be a function of y. So you have to rewrite it as x is equal to the square root of y.
Okay.
Okay, my little radius also has to be a function of y.
Is it going to be x equals 2y?
Okay, solve for it. Is that Rodney?
Yeah.
Okay, so you have y is equal to 2x. Solve for x. What do you get?
Oh, x equals 2 over y.
Almost.
Oh,
What-
wait, no, x equals y over 2.
Good. There you go. Okay. All right. So now we have the volume, the integral, 0 to 4. Remember, even though we found out x equaled 2, we needed the y value. We needed the height. We needed this height, okay, to see where the washer went. Okay. Then we have pi, big radius, square root of y squared minus little radius y over 2 squared dy. So this is the integral from 0 to 4 of pi. I'm going to get y minus y squared over 4 dy. And that turns out to be 8 pi over 3. Okay, so it was brought to my attention by my other class that my homeworks are a little bit off kilter. And that's because, where's my tentative schedule? I think I'm behind. I think I was being very hopeful as to wanting to get through this section in one day, but I just can't. I tried it several times. I just cannot get through this section in one day. Let me see, documents, courses, 252, spring 2020. Tentative schedule had me getting through this section in one day, which is unrealistic. Okay, so that's fine. We're going to be a little bit behind. I switched the homework date. I pushed the homework for cylindrical shells to next week. Okay. Ooh, that means I may need to, nope, I don't need to change the quiz. Great. Okay. Any questions?
So the quiz is still due on this week?
Yes, because the quiz only covers section 1.7 and 2.2. And we completed 2.2.
Okay.
Okay, so yes. All right.